Hello and welcome back to the channel. Today I wanted to explain to you how the AIM-9 Sidewinder works and what its general functioning principles are. My sources for this video are going to be AIM-9D Guided Missile Sidewinder 1C Description, Operation and Handling from the 1st of December 1964. Its document number is NAVWebs OP3352. And the second document is like a little bit of a backup. AIM-9B Guided Missile, formerly Sidewinder 1A, description of and operation, NAVWebs OP2309, Volume 1, 3rd revision, from the 15th of August 1966. Both of them obviously are declassified because they are fairly old. So, the Sidewinder is an infrared guided missile. It is consisting out of several major components. I will split the video in several parts. Let's first of all draw the general missile. Let's make it a little longer and a little thinner. Kind of like this. Is it always a triangle in this direction, or? Like this, and then I do the same thing so, and push it here. Okay, no, this is not perfect. God damn it. And then the back fins are kind of like this. So this is not perfect. It gets close enough for this video. Okay. So in the front, we start with tip to butt, because it's a Navy missile, and well, Navy, you know, funny. In the front, we got the guidance and control section. This is pretty much the heart of the missile, and this is going to be probably most of what the video is going to be about. At the very nose of the guidance and control section, we have the infrared dome. Let's use this color. This is made out of a material that only lets infrared of a specific wavelength through. On older infrared missiles, it was a very simplistic material that, on the older versions of the Sidewinder, it was very simplistic. With more modern versions, this dome was specifically shaped and made out of a material that even blocks out certain frequencies that are used by some flares as a first line of defense against infrared flares. Now let's actually do like a detailed look on what's actually under that dome, because that's our first thing. I'm gonna draw it like this. Kind of like cut open. I think this is a little too small, but we will handle. And below that we have two mirrors. One is right here. Oh no, I need to do this again. One is right here. Okay, well. Okay, one is right here. maybe not quite so close, maybe a little bit back. And the second one is right here. And this one is about a little bit shaped like this. However, the second mirror also has a hole in the middle. So, what's the path that the infrared radiation takes through the set of mirrors? Let's say our target is somewhere in this direction. The infrared radiation comes along this way, bounces from this mirror, and then gets focused down through the hole onto the detector. Let's say we also have some radiation that comes from here, bounces, and then obviously it gets all focused onto one point. Kind of like this. This whole set of these two mirrors both sit on a gimbal. This is like the missile body. So it's like they are like, let's use this for structural stuff. They are like mounted, connected to another. And this whole mechanism, yeah, can move. I don't know how to best draw this. Yeah, kind of like this. This is all connected to another, and they move. It's very similar to how the human eye, or like an eye, functions. Now, what's down here? Because that's where all the infrared radiation gets focused down to one point. At that spot, yeah, let's do it in this color. We have a small infrared collecting diode. It's a single cell diode. So all it can measure is the strength of the infrared signal and like the duration. So like how much infrared light comes in, and it uses this, like it's like a resistant element, kinda. So there you have like a signal coming in, a signal coming out. There's a difference. Then you can know with that stuff. Oh wait, no. The total signal that comes in. This signal is then processed down in like the main computer of the missile, and we will take a look at how that looks like. Oh wait, we use red to visualize stuff. How that looks like on the side. Now, there's a little bit of a caveat, because with just the strength of the infrared signal, you are not able to determine from what direction it comes, because, well, it gets focused down. For that, you need something in front of the sensor. In the case of the AIM-9 Sidewinder, it's a reticle. It sits somewhere in front of the focus point, or on the focal point, and depending on from what direction that infrared signal comes, it's the line of focus, or where it appears on the reticle, shifts slightly. Now, how does this reticle look like? Well, it looks somewhat a little thinner of an outer line would be nice. Like this. It's a round disc. Let's make it perfectly round. And this round disc is split in half along the middle. We have one part of the disc that lets through 50% of all light. right? And then on the other side of the disk, we have a pattern that looks kinda like this. It's like alternating between 0% light, so all light is blocked, 100% light, 0%, 100. Oh, no, I didn't draw it nicely. Oh yeah, there. And it's like this alternating pattern that the missile has. On the original missile, let's actually take a look into the original document. They actually show how the disk looks on the real Sidewinder, roughly like this. So we have here the sections with 50%, with like 150, 150, and here's the section that only lets half the light through. Now this disk, by the way, also here is how the gimbal looks. It's very similar to how I have drawn it. It uses a magnetic gyro. Now, this disk is spinning at a very high rate. And because it's spinning at a very high rate, let's say our infrared source sits right about here. Let's say our missile has an infrared source on this spot. Right about here. Then the missile is able to notice information where this infrared source is by looking at the signal that the flashing light creates because, well, the disk is spinning in front of the sensor. The signal looks... let's just put in like our signal processing box that you probably know from the previous video or with the sparrow. And we have our graph. That's the y-axis. That's the x-axis. Okay, so the y-axis is the the strength of the signal. Let's say it's S, and the x-axis is time. Now, the signal that is being created by this pattern, because it's spinning, looks roughly like this. Right? Let me... 1, 2. I have 2 blips. Wait. Now let's say that the disk is spinning in this direction. This is actually important. Now we have a baseline spot. Let's say this is the baseline is in this direction. Here. And then from there on it calculates the angle. So this would be 90 degrees, this would be 180 degrees, and this would be 270 degrees, right? When the disk spins in this direction, this means that the signal for this infrared spot starts with 2 blips, and the first blip is going to be 0%. So 0% signal, then it goes up to 100% signal, right? Because it... Wait, no, it starts with 100% signal here. Then it goes to stays there, goes down to no signal. I should maybe use a different color for this. Also, I'm probably making a mistake right now, but it will still make sense at the end. Let's use green like in the last video. Yeah, 0 and then 100. So 0, this is the 0 signal. 100. 0. Then we are here. Here, this is the 0 signal. Then 100. Right, then we are here. Then comes the 0 signal. And then we enter this section. It goes down to 50% signal. So 50% of the light comes through. This goes on for a half rotation. Let's say this is about half a rotation length. And then on my example, it would drop to 0% signal again. Then 100. I know this takes a while to draw out, but I want to get it right. Then 0. A 100. 0, 100, 0, 100. And then we start at, and this is like one rotation. Okay. Now, this is one rotation of the disk. Right? Now, based on how this whole block here, this signal block of one rotation is shifted on the x-axis back and forth, the missile knows in what sector the infrared source sits or in what angle. So because in my example, we start with 0, 100, the missile knows that the infrared source sits on this axis here at this angle from our starting point. Let's say this is like, I don't know, 45 degrees. I did make a mistake actually. But yeah, so this means that on the time axis, which could also be changed into like our angle axis, it's very similar because the missile uses like a comparison signal to the original IR signal. The missile then knows, this is the angle at which my infrared source is sitting. Now, based on that knowledge, following happens. The gimbal of the missile turns at the signal, meaning that the infrared spot moves to the center of our reticle. Dang it, I should have maybe made a copy. Well, that's how you learn. I'm gonna simplify it a little bit. Just make it a two-plane thing. Right. So, and now what the missile did, by the way, this would also work when the reticle looks like this. However, then you need perfect conditions. This black or 0, 100, 0, 100 section on the AM reticle, that's called an amplitude modulation reticle because the amplitude is being modulated. This section is there to filter out reflecting light coming from clouds and other stuff of types of clutter. However, for the guidance, a two-piece disk would be enough to tell the missile, oh yeah, this signal comes from here. So what the missile does is it keeps the infrared spot in the center of our disk. And it tries to keep it there. Yeah, fill it out with red. No, yeah. It tries to keep it in the middle. Because what happens when the infrared spot is in the middle, let's say after one rotation the missile changed its signal. So this is like, this is the signal of 1, and then after that it looks like this. Pretty much the signal completely zeroes out. The missile tries to keep its signal at 0 because that's like the perfect state for it. Why is it 0? Well, because the infrared spot is in all segments at once. That's why it is at 0. Now, what happened? What happened is the Seeker gimbal. Let's say this is still our infrared radiation that is coming in. And now our Seeker gimbal looks pretty much straight at it. This is what happened. Let's draw it all neatly out. So we have also the dome. Don't forget the dome. Make it a little rounder. I know it's not perfect, but it gets the job done. And obviously the missile body. So yeah, the infrared radiation then obviously is getting focused right in the center of kind of like this, you know, right at the center. Oh no, this is still red. I want to draw of the sensor. Oh well, of the whole assembly. Okay, now the missile knows in what direction its gimbal is looking. It's using this knowledge and the change of in what direction the gimbal is like tracking to figure out roughly where the target is in relation to the missile. It then tries to go into a proportional navigation intercept course. using the document again, because I'm too lazy to draw it, we have here the missile body, and all of let's make it possible to draw in here, and all of these angles here, this one, this one, this one, this one, and even this one, this one, this one, are all equal. This is a big part about proportional navigation. This is like the lead angle the missile takes, and because all of these angles are equal, the missile stays pretty much on a straight course. Instead, if it would just try to align the gimbal with the missile body, instead of flying like this course that it would do if it would be straight pursuit. So this is the straight pursuit course, and this would be the proportional navigation course. As you see, you would need way less energy to fly this course than it would need energy to fly this course on a intercept. It's far more energy efficient, and the missile actually can lead targets. Very smart. Very smart. How that whole stuff inside the computer works, I actually have no idea. I haven't dug deep enough into the subject matter. However, this is how the seeker roughly functions. However, we don't just have the seeker. Let's actually extend our drawing a little bit down. The missile has fins that make it maneuver. Let's talk about those. About how the missile actually maneuvers. And here we already will see the first major differences between different Sidewinder models. Oh, I forgot one crucial bit. Later Sidewinder models have a cooled detector, meaning a small bit of coolant material or a Peltier electric device is used to cool down the seeker to make it perform much better in detecting infrared sources, and also to filter out some bits of infrared radiation that are unwanted. In the early Sidewinder models, they use a lead sulfide detector material cooled down to 77 Kelvin, and then later, so that's like minus 200 degrees Celsius roughly. And the later Sidewinders, so AIM-9L and M, while also using a different type of reticle. I'm not going into too much detail, I just want to talk about the slightly older models. They also make use of what was indium something INSB is the proper term of that semiconductor that they use to detect the infrared radiation. So we have PBS on the older models, and then it was replaced by this stuff in the later models. And the INSB makes it possible to detect aircraft in a head-on, which gives the Sidewinder the all-aspect capability. Anyway, now let's talk about the guidance fins, or the canards at the front of the missile. These are powered, let's first of all draw them here. Let's make them equal. Mirror them and put them here. The axis of rotation sits slightly forward, and always two wings are connected to another. So they can't move separately to cause like a rolling moment. They only can go either up or down or left and right. So on that axis, we have two opposing pneumatic cylinders. Let me actually draw the internals of the wings that we don't see here. So these are like the wings for up and down, but for this to properly to be explained, I want to make the wings that cause like this motion. So the wings that are here. Four wings, right? Then we have like here our axis of rotation. And on that axis, we have like a metal rod that goes through the axis. And that metal rod is connected with two pneumatic cylinders. Kind of like this. So when this cylinder extends, the wing moves in like this direction. Wait, this direction, and when this cylinder extends in this direction, or when this cylinder retracts, it goes this way, and so on, so forth. Okay, now how are these controlled, or where do they get their pneumatic pressure from? Well, below them, we have a gas generator. It's literally just a pot with a powdered propellant inside that slowly burns off, and this gas pressure is then routed to our pneumatic cylinders. So, however, we only have the routing to the cylinder. We don't have any routing coming back or so. Well, this is done by just two outlet valves that lets their pneumatic pressure of one of the two cylinders out. What happens is quite simple. The pressure in the cylinder where the valve gets opened, let's say this cylinder vents out, the pressure in the cylinder drops, and the total force exerted by this cylinder here is higher. Therefore, let's draw it in this dark red. This cylinder extends and our wing moved in this direction. Now the missile turns that way. Well, turns that way. Quite simple, I'd say. When you want to move in the other direction, because well, our infrared source comes from this, we really just let our pressure out of this cylinder here. So here the pressure gets released. Then the wing swings in this direction. Kind of like this, you know. And the missile turns to the right. So this is generally how all of that works. However, there's a second part to this. Right, let me to this gas generator bit. And that is well, it depends a little bit on the missile. an exact version. But on most of the versions, it is a turbo generator. It's a little turbine that is getting spun by the gas pressure that is then creating electric energy for the missiles guidance and control section. So when we have here all the computer parts, they need electricity. Let's say yellow for power, and that electricity simply comes from our turbo generator. Starting with the AIM-9H model, this turbo generator was replaced by a thermal battery. So it's a different component. The missile no longer has to use up its precious gas generated reserve, which is like limited. Now it uses a different component. This is still in the rough vicinity. However, it is a thermal battery, which is a method of creating electric current based on a chemical reaction when you burn a specific material or gas. Well, and these ones can provide a lot of current for a decent amount of time, however only once, and they are fairly cheap compared to the turbo generator that was used beforehand. So it's perfect for pretty much any missile, and a lot of missiles actually use a thermal battery to power not only the guidance and control section, but also the fuse and everything, really. Now, this is the guidance and control section. It controls the missile, it guides it, it's the brain of the missile and the legs to make it move. Behind that, we got our target detector and warhead section. Let's make it a little shorter. I, by the way, know that I'm already recording for a while. It's the Sidewinder is a more complicated topic. In reality, really, it's just the warhead. And the target detector is really just a spicy tube with explosives inside. So we have here the explosive section. The fuse was in the back. And we have our fuse, which is an infrared detector on the earlier Sidewinders. Later models used a radio frequency detector, and the latest models used a laser to find the target. What it really just is two, or like with the infrared detector, is a bunch of infrared detectors mounted to the side in like a ring, and whenever they find a infrared source, because the missile just passed a jet engine, the detector says, oh, I found something, let's initiate the detonation of the warhead. The warhead detonates, and hopefully the target gets destroyed. Now, this obviously doesn't work with a direct impact, so the missile does have has a backup impact fuse that when you have a direct impact, well, the missile will still detonate, hopefully. Well, one time it didn't, in 1958, when it was first used against China, and that caused pretty much the Eastern Bloc, like Russia, Soviet Union, China, and all of them to get their hands on the Sidewinder and reverse engineer it. Quite interesting, actually. Okay, rocket motor. Fairly simple. It's a rocket motor. There's really not much to it. It's really just a long spicy tube filled with a material that burns down and powers the rocket. On the Sidewinder, it powers the rocket for about, depending on the version, 3 to 5 seconds. Earlier versions usually last shorter, and then they get better rocket motors. Now, if you have a keen eye, you probably have noticed that with the control, there's no roll stabilisation. Well, that is done by the Rollerons. These are mounted to the tip of our rear fins. And let's make them bigger. Kind of like this. That's the rough shape of them. And the Rollerons are a bunch of small wings I like this. That are mounted to the tip of those back guiding vanes or wings. And they have something very special on them because they are really very simple mechanically. Here's the rotational point, and they are really just a inertial wheel that sticks out part of it into the airstream. And because they have these wheels have like a little bit of like teething on them, they kind of look like a gear, kinda. The airstream spins them up to a very high speed. And because they have a certain mass, and because this whole fin is mounted at an angle, here's like the rotational point, so the fin is mounted through here with like some brackets. Whenever the missile rotates along its axis, these wings will move in the opposite direction and will stabilize it, so that the missile, like typically, does not have any rolling motion and is stabilized. Now, it's not a perfect system, but it's a very cheap and very effective system. And the typical maximum roll rate that you can expect from a Sidewinder is about 1 to 5 rotations per minute. And that's really not enough to offset the guidance or anything of the missile too far off. Is there anything else that I missed? Probably not. So let's recap. At the tip, we have our infrared dome that filters out certain amounts of infrared radiation. When the radiation passes through, it gets bounced around in 2 sets of mirrors and gets focused down on a single cell infrared detector. This single cell infrared detector, in front of it, has a amplitude modulation reticle that spins at about 200 rotations per second, incredibly fast. And because it's spinning and has a specific pattern drawn onto it, the missile can use the frequency generated by that pattern to figure out at what angle the infrared source sits on that disk. It then moves the gimbal servos to the spot that the infrared source sits right in the middle of that disk, and then the missile knows, aha, the enemy is in that direction. It then tries to keep this angle here, let me draw it in, Let me use dark blue for that. It tries to keep this here, this angle between the missile and the missile body constant for a proper course in proportional navigation, so that it bleeds as little energy as it has to, because the energy that it has to bleed for maneuvers is means that it has less energy for its gas generator, or generally it has less space to maneuver because its ability to maneuver is limited by the amount of gas that is generated by the gas generator. When the missile then passes the enemy, on the older models, a infrared proximity fuse senses that the missile passed the engine of the enemy aircraft and then initiates a detonation. On more modern missiles, they use either a laser, so like a laser that's slightly pointed to the front, or a radio proximity fuse to do the same. To not have the missile roll on its axis, it is using a Rolleron, which is pretty much just a swing wheel that is mounted into a free swinging wing, and that is powered by the airstream of the missile going about Mach 2. This fast rotation causes the missile to be stabilized because the wings deflect in the opposite direction of the roll of the missile. All in all, the Sidewinder is a very capable and cheap weapon system that pretty much revolutionized modern air combat. If you want to learn more about other missiles, as maybe you want to watch my video on the AIM-7 Sparrow. For that, just click here, somewhere here. If you want to see a random video on my channel, click here. And if you want to subscribe, click here. I hope you enjoyed this video, and we see us in the next one. Bye bye everybody.